The moment people hear the words black hole, a quiet panic sets in. They imagine a place where everything disappears, where light itself gives up, where time somehow stops working. Very quickly, a sentence forms in the mind. This must be where physics breaks. That reaction is natural because black holes seem to insult everything we learn from daily life. Objects fall, but not forever. Light travels, but it can't just vanish. Time moves forward, not sideways or backward. Black holes appear to ignore all of that, so we assume something must be wrong with the laws of nature. But this is where Richard Feynman would slow the conversation down. He would say that before accusing nature of being inconsistent, we should ask a harder question: what exactly do we mean by physics? Physics is not the universe. Physics is a human-made description of how the universe behaves. It is a set of ideas, experiments, equations, and approximations that work remarkably well in most situations. When those descriptions feel uncomfortable, it does not mean reality has failed. It means our description is being pushed beyond familiar territory. We are very good at mistaking our explanations for the thing being explained. When an equation works, we trust it. When it struggles, we panic. But nature does not care about our comfort. Nature simply does what it does. Black holes feel disturbing not because they are violations, but because they sit at the edge of where our everyday intuition stops helping us. They are extreme cases, and extreme cases always make simple explanations look fragile. Think about something ordinary like speed. For most of human history, speed seemed limitless. You could walk faster, run faster, build better horses, invent engines. Then physics quietly reveals that there is a maximum speed built into reality. Nothing with mass can reach or exceed the speed of light. That discovery did not mean physics broke. It meant we discovered a boundary we didn't know existed. Black holes are similar. They are what happen when gravity reaches a boundary condition we rarely encounter. Another problem is language. Words like nothing escapes and everything collapses sound violent and absolute. Language pushes us toward drama, but physics is often subtle. A black hole does not announce itself as a place where rules stop applying. From far away, it behaves like any other object with mass. It pulls, it orbits, it interacts. The same laws that describe planets and stars also describe black holes. The equations don't suddenly explode in protest. They simply lead to unfamiliar conclusions. Feynman often emphasized that not understanding something is not a failure. It is the normal state of science. Confusion is not evidence that nature is broken. It is evidence that we are learning something new. Black holes are uncomfortable because they force us to confront the limits of human intuition. They remind us that the universe was not designed to be easily pictured by brains evolved to avoid predators and find food. So when someone says black holes are where physics ends, the more accurate statement is this: black holes are where our simple stories end. Physics does not stop there. Only our ability to explain it in everyday terms does. That distinction is the key to understanding why black holes don't break physics at all. When people talk about physics, they often speak as if it were the universe itself, if equations were carved into reality like laws written on stone. Richard Feynman constantly pushed back against this way of thinking. Physics is not the thing. Physics is our attempt to describe the thing. That difference sounds small, but it changes everything, especially when we talk about black holes. An equation is not nature. It is a tool. It is a compressed summary of patterns we have observed. When an equation works, we celebrate it and begin to trust it deeply. Over time, we forget that it was invented by humans, tested by humans, and limited by human imagination. Then, when the equation reaches a place where it becomes difficult or gives strange answers, we react emotionally. We say something must be wrong with the universe, but it is far more reasonable to suspect that our tool has reached the edge of its usefulness. A simple analogy helps here. Imagine using a map of your city. The map is incredibly accurate for streets, buildings, and routes you travel every day. If you suddenly try to use that same map to navigate the inside of a building, the map seems to fail. It shows no stairs, no hallways, no rooms. The building did not break the map. The map was never meant to describe that level of detail. Physics works the same way. Our theories are maps, not territory. Black holes push our maps into regions they were never designed to handle comfortably. The equations of general relativity work beautifully for planets, stars, galaxies, even for black holes viewed from the outside. They predict orbits, gravitational waves, and time dilation with astonishing accuracy. Nothing about black holes forces us to throw these equations away. The trouble begins when we ask questions that go beyond what the theory was built to answer, such as what happens at infinitely small scales, or how gravity behaves when quantum effects dominate. Another source of confusion is that mathematics feels authoritative. Numbers look precise. Symbols look final. When math speaks, it feels like reality itself is speaking. Feynman warned against this psychological trap. Mathematics is a language. Like any language, it has limits. When the math produces infinities or undefined behavior, that is not a declaration that reality has become infinite or undefined. It is a signal that the language is being stretched too far. Humans are especially vulnerable to this mistake because our brains crave certainty. We want clean answers, sharp boundaries, and final explanations. Black holes refuse to cooperate with that desire. They sit in a region where multiple descriptions overlap, where classical ideas about space and time begin to blur, and where quantum ideas have not yet fully connected with gravity. Instead of accepting that our understanding is incomplete, we often declare the situation paradoxical or broken. Feynman would remind us that this discomfort is not a problem to eliminate, but a clue to pay attention to. Science grows precisely at these uncomfortable edges. When our descriptions strain, it means we are learning something important about the world and about the limits of our thinking. Black holes are not evidence that physics is wrong. They are evidence that physics is still a work in progress, refining its language to better match a reality that is deeper, stranger, more consistent than our current explanations can fully capture. Before black holes ever entered the conversation, gravity was already one of the strangest ideas in physics. We are so used to objects falling that we rarely question what is really happening. A stone drops, the moon stays in orbit, planets circle the sun, and it all feels natural. When physicists tried to explain gravity deeply, the explanations became anything but simple. For a long time, gravity was described as a force. Newton imagined objects pulling on each other across empty space. That picture worked extremely well for everyday life and even for predicting the motion of planets. It carried a hidden mystery. How does one object know that another object is there? How does the pull travel across space? Newton himself was uncomfortable with this idea, even though his equations worked. Einstein changed the story completely. He proposed that gravity is not a force acting through space, a change in the shape of space and time themselves. According to this view, massive objects like stars and planets curve space-time around them. Objects moving nearby simply follow the straightest possible paths through that curved space-time. What we experience as gravitational attraction is really motion through a bent geometry. A common analogy helps make this idea less abstract. Imagine space as a stretched rubber sheet. Place a heavy ball in the center and the sheet curves downward. Roll a smaller ball nearby and it spirals toward the heavy one. The smaller ball is not being pulled by an invisible string. It is just following the curved surface. The analogy is imperfect, but it captures the essential idea that geometry, not force, is doing the work. Once gravity is understood this way, black holes stop looking like violations of physics and start looking like extreme examples. A black hole forms when a large amount of mass is squeezed into a very small region. The curvature of space-time becomes so steep that all possible paths lead inward. Even light, which always travels at the maximum speed allowed by nature, cannot find a path that leads away. This is not because light slows down or gets tired. It is because the shape of space-time itself leaves no route for escape. This point is crucial and often misunderstood. Light does not break its own rules near a black hole. It still moves at the same speed it always does. The laws of physics governing light remain intact. What changes is the geometry through which light is moving. In a strongly curved space-time, what counts as forward can point inward just as naturally as it points outward elsewhere. From far away, a black hole behaves like any other massive object. It has a gravitational field, it influences nearby orbits, and it responds predictably to physical laws. There is no sudden region where equations stop working. The same framework that explains gravity around Earth also explains gravity near a black hole. The difference is one of degree, not kind. Our discomfort comes from intuition, not from physics. We are used to thinking of space as a passive stage where events happen. Einstein showed us that space is an active participant. Black holes simply reveal this truth in its most dramatic form. They do not overthrow gravity. They fulfill its logic to the extreme. And when gravity is seen this way, black holes no longer look like exceptions to the rules, but like the clearest demonstrations of how those rules truly work. One of the most persistent misunderstandings about black holes is the idea that they contain a sharp boundary where the laws of physics suddenly change. Boundary is often imagined as a kind of invisible wall, a deadly edge where everything instantly falls apart. In reality, the situation is far quieter and far more subtle. The so-called event horizon is not a physical surface. It is a boundary defined by geometry, not by material or force. To understand this helps to think in terms of motion rather than objects. The event horizon marks the region beyond which all possible paths through space-time lead inward. From the outside, looks like a point of no return. But from the perspective of someone falling toward it, nothing dramatic happens at that exact location. There is no flash of light, no sudden pressure, no clear signal announcing that a line has been crossed. Locally, the laws of physics remain the same as they were moments before. Difference in perspective leads directly to confusion about time. It is often said that time stops at a black hole. What really happens is more nuanced. Time does not behave as a single universal flow shared by everyone everywhere. In Einstein's picture of reality, time depends on motion and gravity. Clocks in strong gravitational fields run differently than clocks far away. Imagine two identical clocks. One stays far from a black hole, and the other moves closer and closer to it. The distant observer, the clock near the black hole, appears to tick more slowly. Signals sent from it take longer to arrive, and each tick is more stretched out than the last. From far away, it can look as though the clock never quite reaches the event horizon at all. But for the person carrying that clock, nothing strange happens. Their heart beats normally. Their thoughts proceed at a normal pace. Their clock ticks just as it always has. Both descriptions are correct, and neither contradicts the laws of physics. The disagreement arises because time itself is not absolute. It is woven into the structure of space-time and depends on the observer's situation. This idea is deeply uncomfortable because human intuition demands a single answer to the question, what time is it really? Physics does not provide such an answer. Instead, provides relationships between different observers. Near a black hole, those relationships become extreme, but they do not become inconsistent. The event horizon, then, is not a place where physics breaks down. It is a place where our everyday language breaks down. Words like before, after, inside, and outside lose their simple meanings. Mathematics remains consistent, but the story we tell ourselves becomes harder to phrase in familiar terms. Black holes force us to confront a difficult idea. Reality does not organize itself around human intuition. The universe allows multiple, equally valid descriptions of the same event, depending on how and where it is observed. The event horizon is not a cosmic glitch. It is a reminder that space and time are far more flexible than our instincts suggest, and that physics continues to function smoothly even when our preferred ways of thinking fail to keep up. The center of every black hole lies the idea that makes physicists the most uneasy, the singularity. According to our current equations, all the mass of the black hole is compressed into a region of zero size, where density and curvature become infinite. The word infinite immediately raises alarm bells in physics. It is not a comfortable conclusion. In fact, it is usually a sign that something important is missing from the description. Richard Feynman often pointed out that infinities are not answers, they are warnings. When a calculation produces infinity, it usually means that a theory is being pushed beyond the range where it was meant to apply. The theory has not necessarily failed, but it has reached the edge of its usefulness. The singularity inside a black hole should be understood in this spirit. It does not tell us that reality literally contains infinite density. It tells us that our current understanding is incomplete. What makes this especially tricky is that our best theories work extraordinarily well on their own. General relativity describes gravity and large-scale structure with incredible accuracy. Quantum mechanics describes particles and small-scale behavior with equal success. The problem is that these two theories speak very different languages. When we try to use general relativity to describe extremely small regions, such as the center of a black hole, begins to produce infinities. When we try to use quantum mechanics to describe gravity, it does not yet give us a complete picture. This mismatch is not unique to black holes. Black holes make it impossible to ignore. They bring the two theories into direct conflict. At the center of a black hole, gravity is strong and scales are tiny. Both theories demand to be taken seriously, yet they do not fully agree. The singularity marks the point where we know our tools are insufficient. Despite this is a great deal we do know about black holes. From the outside, they are remarkably simple objects. They are fully described by a small set of properties, such as mass, spin, electric charge. They obey conservation laws. They grow by absorbing matter and energy in predictable ways. They emit gravitational waves when they collide. None of this behavior violates physics. In fact, it confirms our theories with impressive precision. What we do not know is what happens at the deepest level of space-time. We do not yet have a theory of quantum gravity that tells us how space and time behave at the smallest scales. Various ideas exist, but none have been confirmed experimentally. Until such a theory is developed and tested, the singularity remains a placeholder, not a physical object we can fully describe. Human discomfort with this uncertainty is understandable. We like explanations that feel complete. We prefer to believe that science provides final answers. Black holes challenge that belief. They remind us that scientific knowledge is always provisional, always subject to refinement. This is not a weakness of physics. It is its strength. The singularity does not represent a breakdown of the universe. It represents the boundary of our current understanding. Beyond that boundary, reality continues to exist and behave consistently, even if we do not yet know how to describe it. Black holes do not shatter the laws of physics. They quietly point toward the next layer of those laws, waiting for us to learn how to see them.